Hi, and welcome to IRMS Basics, where we will discuss what IRMS means and the science behind it. This series, we will be discussing what IRMS stands for. IRMS stands for Isotope Ratio Mass Spectrometry. But what does that actually mean? Today, we will be discussing isotope ratios and why they matter. If you need a refresher on what isotopes are, please watch our previous video called What is an Isotope? Now let's get down to business. As discussed in our last video, different isotopes won't act differently chemically. They make the same chemical reactions. So why bother looking at them? There are many different reasons someone would want to look at isotopes. They can help us understand plants, animals, soils, clouds, volcanoes, almost anything you can think of. But we only have a few minutes for today's video, so let's discuss water. Ultimately, the reason isotopes matter is because different weights can affect how easily something reacts. Imagine you're taking in the groceries, and your siblings are coming to help. If you're tired, you would grab the bag with the bread or the chips and leave the bag full of heavy cans for your siblings. In this case, the bread is picked up first because it's lighter. The same works with water. When water evaporates in the cold, it prefers to pick up the less heavy water because it doesn't have the energy to pick up the more heavy water. It doesn't bother to pick up the heavy water until it's warm and it has the energy for it. In our last video, we discussed how hydrogen can have a mass of either 1 AMU or 2 AMU. Let's see how that looks when in water. Water has 2 hydrogens and 1 oxygen. In this case, we have a water molecule where both hydrogen isotopes have a mass of 1 AMU, and our oxygen has a mass of 16 AMU, so our water's total mass is 18 AMU. Over here, we have a water molecule with 1 hydrogen isotope that has a mass of 1 AMU, 1 hydrogen isotope that has a mass of 2 AMU, and an oxygen that has a mass of 16 AMU. Our total mass for this water is 19 AMU. In this case, the water with 18 AMU is known as light water, and our water molecule with 19 AMU is known as heavy water. The ocean is filled with a lot of this light water and a lot of this heavy water. When the water evaporates, the powers that be, the ones that pick up the water molecules, pick up the light water molecules first. If it's warm out and they feel like they have the energy, they'll pick up the heavy molecules too. Now there's a cloud with a bunch of light water and a bunch of heavy water. When the cloud moves over land and starts cooling down, it'll start dropping the heavy stuff first in the form of raindrops. It'll continue until it's happy with the amount of weight it's holding. When the cloud continues moving inland and eventually rains again, it'll be full of light water and will be really low on heavy water. This gives us a range of heavy isotopes near the coast and in warmer areas, and light isotopes inland and in colder areas. Scientists all over the world sample water every year to keep track of these isotope ratios and map them out. Remember this saying, "You are what you eat"? This saying applies in isotope research. Now that we've tracked what the water isotopes are like worldwide, we can look at the plants and animals that drank that water, and they'll have similar isotopes to what they drank. Scientists can now use this to track animal migration or see where plants came from. There's many more reasons to look at isotope ratios. If you want to learn more, push the subscribe button to keep up to date with new videos where we'll explain other uses for isotope ratios. For now, thank you for watching and tune in to our next video on the other part of IRMS, mass spectrometry.